Hello and welcome. I am Dr. Anil Joshi. Welcomes you to my series Learn Radiology with Dr. Anil Joshi. Today's topic is on MRI physics, that also on Larmor frequency. It's one of the very important topic we are going to cover in this lecture briefly. A detailed information equations are required which are given in some other lecture. So today we'll see in a condensed form Larmor frequency, what it is and what effect it has got over the MRI image production. So let's get going, but before we have to disclose acknowledgement and disclaimer. This is an educational series and it has got no commercial outcomes. Whatever material we are using in the lecture is from our department, which we use for routine lectures. However, some of the material has come from net, but we are confirmed that it is royalty free. With that, we thank them, acknowledge them, and we start our lecture on the MRI physics. So today's topic is Larmor precision. Larmor precision, it is a precision of the magnetic moment of a external magnetic field. Precision and reliability are important factors to consider when investigating a utility of measurement technique. So here what is a technique is MRI. Now we have to confirm the reliability of the parameters we are using. So it is also important. So both the things. Now going further, Larmor frequency is the equation stating that the frequency of precision is directly proportional to the product of magnetic field strength and gyrometric ratio. So what are the two important factors in Larmor frequency? Magnetic strength and second is gyrometric ratio. Gyrometric ratio will be referring as G is the ratio of the magnetic moment to its angular momentum. Now there is an angular momentum and there is gravitational force. Now this we are going to demonstrate this principle with the help of a spinning top subsequently. Now there is another additional terminology, Thomson's precision. It's a relatively correction that applies to the spin of the elementary particles of the rotation of the macroscopic gyroscope and related to the angular velocity of the spin of a particle following a curvilinear orbit to the angular velocity of the orbital motion. It's slightly difficult to understand, but we'll make it easy once we see all these things, illustrations. Now let's see the illustrations. This is a spinning top which will demonstrate you. It has got a angular momentum in which it is moving and there is vertical gravitational force. When the ratio will be disturbed, it will collapse. So this is the main principle, that angular momentum, then gravitational force which is vertical against its stability. Now here again we are explaining it in more detail. You can see the first spinning top is wobbling. Wobbling is precision. Now you are seeing the three diagrams. In that, one is in rotation, that is in the angular momentum. The second is in a steady rotation and third is wobbling. Now these three things depend on the angular momentum and gravitational forces. The best way to visualize motion of a nucleus is to see motion of a spinning top. They will give you an idea how there are movements in the nucleus. Now the spinning top spins around itself and due to gravity it precesses. Now precision is, as I told you, is a change in axis. So it will change its axis over the time when it will have less and less angular momentum, and ultimately when there is no angular momentum it will succumb to the gravity. Now here again we are seeing same example in different ways to get the idea about the precision in proper ways. Now you can see the change in axis as well as rotational. Let's revise precision. It's a change in direction of the axis of rotation of the spinning angular momentum. The nuclei processes around the magnetic field for essentially the same reason as that of the gyroscope process around how the gyroscope processes around a gravitational field. So there is gravitational field which is vertical and a gyroscope spins around. This is the same as that of the nucleus, and that's why we have shown you as a diagrammatic presentation. Both gyroscope and nuclei possesses angular momentum, that is the momentum they have achieved because of the angular speed. For the gyroscope, angular moment results from a wheel fly rotating about its axis, and for nucleus, angular momentum results from an intrinsic quantum property, that is the spin. The momentum is also sometimes called as inertia. Now Larmor frequency. The Larmor precision frequency is the rate of the precision of a spin under the influence of magnetic field. The frequency of RF signal will cause a change in the nuclear spin. Now what is RF signal? Who produces them? How they are produced? In which axis they are produced? There are extensive lectures on this topic. Do visit our website for that. So to summarize, the frequency of an RF signal will cause a change in the nuclear spin energy level, and it is given by the Larmor's equation. The frequency is determined by the gyromagnetic ratio of the atoms and strength of the magnetic field. So which are the two factors controlling it? Is the gyromagnetic ratio of atom, and second is strength of a magnetic field. So these are the two things which will contribute towards Larmor's frequency. The gyrometric ratio is different for different nucleus of different atoms. Now this is a beneficial to us. Since they are different, the Larmor frequency will be different, the tissue characteristic will be different. For protons, the Larmor frequency is 42.58 megahertz. Coming continuous with the Larmor frequency. The stronger the magnetic field, the higher the precisional frequency. If an RF pulse is applied to the nucleus of an atom, the protons will alter their alignment from the direction of the main magnetic field to the direction opposite to the main magnetic field. As a proton tries to regain with the main magnetic field, it will emit energy, and this is the Larmor frequency. How much energy it will emit will be decided by the Larmor frequency, and how much energy it will emit by the equation of Larmor frequency will determine what will be its signal on the monitor, whether it will be bright, that is white, or it will be dark, that is the gray. So that's how the characteristics are defined. By varying the magnetic field across the body with a magnetic field gradient, the corresponding variation of the Larmor frequency can be obtained. Now here we are again going into details of it. The spin is represented by atomere. The circular one with arrow showing movement is a spinning atom. The tip of the arrow presents similar to the tip of the gyroscope. This spin allows absorption of a photon frequency which is dependent on the strength of the magnetic field applied to the nucleus. Now when the applied magnetic field will be stronger enough, the proton axis will regain its direction. It will go to its original position. Now resonance and Larmor frequencies. Proton in a magnetic field have a microscopic magnetization and act like a tiny titops at wobble. That is, we have seen how the spinning top is wobbling. They are like that. That's why we have shown you it at the beginning of the lecture. The rate of the wobbling of the precision is the resonance of the Larmor frequency. Now, in the magnetic field of MRI scanner at the room temperature, it is approximately the same number of protons nuclei aligned with the main magnetic field B0 as a counter aligned. Continuing resonance and Larmor frequency, for every 1 million nuclei there is about one extra aligned with B0. Now B0 axis is the one which has got a magnet axis, that is a table. So in resting phase, B0 axis represents same as that of the table axis. The resultant is a net or macroscopic magnetization pointing in the direction of the main magnetic field. Exposure of the individual nuclei to RF radiation, that is B1 field, at the Larmor frequency cause nuclei in the lower energy state to jump into higher state because they gain the energy. Now in magnetic resonance, the Larmor frequency is determined by the geometric ratio of the particular magnetic moment. In this case, we are looking at a hydrogen nucleus. They are abundant in the body and they are the main source for the MRI. Now what is the chemical shift? Chemical shift is defined as the fractional shift in Larmor frequency in parts per million, that is ppm, shortly referred as. This value increases with the increasing magnetic field strength. This can sometimes cause artifactual voids in the MR imaging. Now you know whether they are used. It is used constructively, means usefulnessly in a spectroscopy to obtain information about chemical binding. Again, this lecture we have covered in some other lecture series. Do visit our YouTube channel for this. Now in MRI, we are looking at the behavior of millions and millions of proton magnet. The net direction of this movement is referred to as the net magnetization, that is vector m. Since more protons are pointing at B0, m points in the direction of B0. This direction is typically referred to as the z-axis. Now we are coming to a z-axis. There is no net polarization in x or y axis. So it is important to know that xy no polarization and it is at the z-axis. The simplest version of the MRI sequence involves a so-called 90-degree pulse. This pulse of the energy is exactly enough to rotate the proton 90 degrees. So the net magnetization rotation from the z-axis parallel to B0 into xy plane. At this point, the magnetization along B0 is also 0. Note, if less energy is given, there will be a rotation less than 90 degrees, which is used in a gradient echo sequences. Alternately, a 180 pulse may be employed to flip the M vector into the Z direction. So, how these sequences gives you different type of images, now you will come to know with this. The pulse is twice as strong, the pulse is twice as long or strong as 90 degrees pulse and is used for inversion recovery sequences. So some of the other places they are useful. The objects possesses momentum and have a tendency to maintain their motion unless acted upon by external forces, like a speeding truck, you know this example, has a great deal of linear momentum and cannot easily be induced to change its speed or direction. Angular movement behaves similarly, conferring to the nucleus of gyroscope a strong resistance to the changing its orientation or the direction of the rotation. Static gravitational and magnetic fields create a torque or twisting force acting perpendicular to both the field and the direction of the angular movements. As the RF electromagnetic ratio is sent through the patient, the atomic nuclei in the body will absorb the energy. This absorption of energy causes nuclei to change in the direction of the spin. If you transmit energy into the system at the resonant frequency, you can change the turn protons away from B0. After some time, this proton will relax and give off energy to return to the lower energy state. This energy will be given off at the time of the frequency in the form of signals which we measure. So, got it? How exactly it is important to know Larmor's frequency, Larmor's precision in image formation. For summary, we have seen in detail Larmor frequency, Thomas precision, precisional frequency, and with that we are coming to end of this lecture. I hope this lecture will be of some help to you. I thank you for giving me your valuable time. Please visit our website for comprehensive and detailed lecture on this topic and also many other. Thank you, goodbye, and take care of you and patients. See you again in next lecture.